In this video, let us talk about ensembling techniques. Suppose if you would like to purchase a new car, you just don't directly go to the car shop and purchase. Before, you'd likely browse a few web portals where people have posted their reviews and you may compare different car models and you may check their features and prices as well. And you will probably ask your friends, colleagues for their opinion, right? In short, you wouldn't directly reach a conclusion. Ensembling models in machine learning operate on a similar idea. They combine the decisions for multiple models to improve the overall performance. Now, let's look at here. Here, so far, we have seen one classification, we have seen classification and regression problems, right? And we have one algorithm for classification, and for one algorithm, we have classification and regression model. Right, so far we have seen this, and we have seen a lot of algorithms like linear regression, logistic regression, decision tree, KNN classification, naive Bayes. Right, now here is the question. Can we solve a problem by using a multiple algorithms? Multiple algorithms? Answer is yes. We can solve a problem with multiple algorithms. Now, here is a ensembling technique for that. So ensembling technique is divided into bagging and boosting. Now let us take an example for bagging. Let us take an example for bagging. Suppose we have a data set here with a number of rows and columns. Let us take a data set here. Okay. Let us say we have many rows. We also have columns. Okay. So we have this as our data set. Now, here I would like to use a model M1. Let us say our model M1 is logistic, logistic regression. Okay. Now let us say that we are using a classification. We just wanted to use a classification problem. So here we have logistic regression. Now our model 2 has suppose a decision tree classifier, and model 3 has KNN classification, and our model 4 has naive Bayes. So we have this different algorithms here, right? Now what I would like to do here is I would like to take the row sampling from this main data set, which will go to my model 1, model 2, some rows will go to model 3, and some rows will go to model 4. So here when I'm saying row sampling, it may also get repeat from model 2 to model 1. So row sampling. Let us say our row sampling here is D dash, this is D double dash, D triple dash, D 4 times. Now these are all row samplings. Suppose we have a data set with 10,000 samples. Okay. Now here when we are using a sampling, it should be less than 10,000, right? Let us say we have some thousand samples. Let us say this is having 1,000 samples. That means our our samples in the model must be less than main data set. Okay, so here we have different algorithms that are arranged here in parallel, and these samples can be also repeated in every other model. Now here I would like to send a test data, like to send a test data and would like to predict my output here with respect to each algorithm. Now for a classification problem we have generally with 1 or 0 as an output. Suppose by using a logistic regression I have got 0. By using decision tree I have got an output called 1. Suppose with KNN classifier we have got an output 1. Naive Bayes we have got an output 1. So here majority voting will be considered. Whatever that comes on the majority voting, that will be our output. So here our majority voting is 1. Majority voting is 1. So our output will be 1. This is so simple. Now suppose if we don't really get equal number of outputs here. So you may say that if we get like 0 0 1 1, what if? Okay, see here we are trying to use some hundreds of models, right? So the more probability will there won't be high probability of getting equal number of ones and equal number of zeros. There should be definitely a difference, right? Now this is for a classification problem. So what if for a continuous value? What if for a regression problem? So for regression problem, it's quite easy. Generally, we will have, and suppose we have got some value here. Let's say we have got 120. Here we have got 140. Suppose here we have got an output of 122. Here we have got 148. In this case, we'll take the mean of all these values, mean of all these values, and that will be our output. Very much simple. And while doing this prediction, we generally count it, right? That is actually also called as bootstrap. We do here bootstrap aggregation, bootstrap aggregation, bootstrap aggregating, right? Now let us talk about a boosting. In bagging we have M1, M2, M3 in parallel. Now here in boosting we have models M1, M2, M3 and M4 in series. So these are all weak learners. Individually these are all weak learners, but together they are strong. Together they are strong learners. For an example, suppose if a student is good in physics, okay, may not be good in mathematics, may not be good in mathematics, may not be good in chemistry, may not be good in biology. So each student individually is good in physics, mathematics, chemistry, and biology. But together they are very strong. So together they are very strong. So this is just for an example. So here we perform we'll just send some data here to the model 1. It may not perform well with everything. It may perform well with some part of the data, and model 2 may perform well with some part of the data. Model 3 may perform well with some part of the data. So like this we have a small performances together combines and give a good performance. This is about a boosting technique. Now here we have classified bagging into here we have classified bagging into two types. The first one is random forest classifier, and the other one is random forest regression. Similarly, in boosting, we have classified boosting into three types. One is ADA boost, second one is gradient boost, and third one is XG boost, which is extreme gradient boost. All right. Now we talk about random forest classifier, regressor, ADA boost, gradient, and extreme gradient boost in our next future videos. Thank you for watching.